Hello, this is Will White. Welcome to this lesson where we are going to compare different battery types and review some sizing considerations that we need to keep in mind when we are designing our battery-based systems. Here's a table. We're going to look at a bunch of different sizing criteria and compare lead-acid flooded batteries, lead-acid valve regulated, which is gel batteries and AGM batteries. We'll look at lithium-ion nickel manganese cobalt and lithium-ion lithium iron phosphate. When we look at cycle life, both lead-acid batteries have a relatively low to moderate, if you get a higher quality battery, cycle life. Both lithium-ion batteries have a high cycle life. That's one of the key benefits of lithium-ion batteries. Our maximum depth of discharge, or DOD, lead-acid batteries can't be discharged all the way, or it really has a negative impact on the cycle life, so we consider that a low to moderate maximum depth of discharge. Whereas both lithium-ion batteries, we can discharge a large percentage of the capacity of that battery with almost no impact on the cycle life. How much of an impact that will have and what the maximum depth of discharge is going to vary by the specific lithium-ion battery. Efficiency for lead-acid batteries, both relatively moderate, somewhere in the 80 to 85% range usually. Lithium-ion batteries are comparatively much higher. The efficiency for lithium-ion ranges somewhere in about the 90 to 95% range, although some manufacturers claim even up to a 98% efficiency. Upfront costs for lead-acid batteries are relatively low. They've been around for a long time. Their costs are relatively stable based on their raw material price, but they are relatively low. There are some valve-regulated lead-acid batteries that are a bit more expensive. Lithium-ion, on the other hand, comparatively have a high upfront cost. The cost of lithium-ion is going down, but they're still more expensive upfront when compared to lead-acid batteries. Now, when we look at the cost over the life of the battery, flooded lead-acid batteries are pretty moderate. Valve-regulated lead-acid batteries are higher because their upfront costs tend to be more expensive than flooded lead-acid, and their lifespan is comparatively shorter to most flooded lead-acid batteries. Lithium-ion batteries have a low to moderate lifetime cost because even though their upfront cost is high, we typically get a large number of cycles out of these batteries, which means we get a large number of kilowatt hours out of the battery, which when amortized over the life of the battery is relatively low cost per kilowatt hour compared to the lead-acid batteries. The self-discharge rate for flooded lead-acid batteries is fairly moderate. It is relatively low for both valve-regulated lead-acid batteries and lithium-ion batteries. If you have a situation where they're going to be sitting in a full state of charge, for example, a battery backup system where they're waiting for a power outage, the low self-discharge rate will add to the overall efficiency of the system. Energy density of lead-acid batteries is relatively low. They take up a large amount of space for the capacity. When you compare them to a lithium-ion battery of the same capacity, the lithium-ion batteries are both going to be much more energy dense, especially the NMC batteries, the nickel manganese cobalt. They have a very high energy density. When we look at the applications that these are most commonly used for, flooded lead acid we see the most often in off-grid systems because they are relatively robust. If we're cycling them on a regular basis, flooded lead acid batteries make a good fit for that application. Valve-regulated lead acid batteries will occasionally see them on off-grid systems, especially systems that aren't going to be maintained regularly. We more commonly see them for battery backup systems, where they'll sit in a float state of charge and they're only used occasionally. Lithium-ion batteries, both types, are being used for both off-grid systems, backup systems, or standby service, and advanced functionality, things like peak load shaving, time of use demand shaving, the frequency regulation, and especially on larger utility scale systems, we're seeing a lot of lithium-ion batteries. Other things that we need to think about with flooded lead acid batteries, there's going to be some maintenance involved. The electrolyte is going to need to be replenished with distilled water on a regular basis. There is no maintenance as far as adding distilled water to the electrolyte for any of the sealed batteries, the valve regulated lead batteries, or either of the lithium ion batteries. All lithium ion batteries designed to be integrated with PV systems require a battery management system. That is both a safety feature, it gives us some really good monitoring metrics, but also it's another point of failure in the system potentially. When we look at sizing our battery systems, many of the choices that go into battery bank sizing are up to the designer or the customer. Things like, what is the maximum depth of discharge? How many days of autonomy do we need? What's the load analysis? And then what's the best battery type for the situation? That's really going to vary depending on the application. If we are doing daily cycling applications like standalone off-grid systems, or systems that are doing advanced functionality like peak load shaving or time of use demand reduction, we're going to use a battery that's going to do well with regular cycling. If it's going to be a battery that's going to sit at a full state of charge and only be used every once in a while, we might use a different battery type for that application. A lot of times customer preference and especially their budget will come into play. If they can't afford the upfront cost of a lithium-ion battery, then that option is going to be off the table. Installation location has a lot to do with battery choice. We have an instructor here at SEI who does a lot of off-grid systems in the high mountains in Colorado. They do not use lithium-ion batteries because the risk of the seasonal use cabin getting below freezing is pretty high. So they wouldn't be able to charge that battery if it's below freezing, so they don't install lithium-ion batteries. We have other installers who work in other regions of the country where all they do is lithium-ion batteries. So how that battery is going to be used has a big impact on our battery choice. Other things like available space. If we're space constrained, maybe we use a lithium ion battery that has a high energy density. And also elevation. Some warranties have elevation restrictions in them, so you can't use the battery above a certain elevation. That's something that you would need to research and ensure isn't going to be an issue with the battery you're choosing and the site where you're working. Key points for this lesson: there are a bunch of different battery types, and there's nuances between batteries within each of the types. Not any one battery is good for all applications. Each shine in different use cases. So you need to figure out what your use case is going to be and pick the best battery for that application. There's a lot that goes into sizing batteries. We need to think of things like depth of discharge, days of autonomy, cycle life, warranty, and a lot of the choices are really up to the preference of the designer. Maybe they have a relationship with a distributor that carries a certain battery brand or type. Those things go into the design of this system, and there's not cut and dry answers or right and wrong answers for what the best battery choice is. One person may design a system using a flooded lead acid battery, and a different person might design that exact same system using a lithium ion battery. There's lots of different reasons to go with different battery choices, and not always a right or wrong answer. So I hope this gave you a little information on battery comparisons and what goes into battery sizing. Thank you for joining us, and I hope you have a great day.